Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about what's called the empirical formula and how we can find the empirical formula from percent composition. So typically when I teach this lesson, I like to use a fun little anecdote about a time that I let a student fill my water bottle for me. So last year when I was teaching my students, or I guess it was 2 years ago, about gram formula mass, I was really thirsty. I don't know if you guys know this, but teachers obviously just can't leave the classroom to go get water. So I asked my students to refill my reusable water bottle, and so a student was kind enough to go do that for me. And when the student came back, they had 2 bottles. And so what had happened was a student had grabbed another container for me from Mr. Clark, who is our lab specialist, or our former lab specialist, and he had asked the student to give the bottle to me. So the student comes back with 2 bottles, and they have labels on them of the following. Okay, they have bottle number 1 has the label that says it's made of 11% hydrogen and 89% oxygen. And the second bottle has a label that says it contains 5% hydrogen and 95% oxygen. Okay, and so I want to know which one of these is actually safe to drink. Now, obviously, this isn't a real story, right? But my student really was kind enough to fill my water bottle for me. But it does kind of help us put us in a position of wondering or answering, I guess, the question of why would this ever be important. So it's important to be able to analyze your samples to understand what they're made of, because from that percent composition, we're able to find out what the chemical formula is. Now, more specifically, we're going to be able to figure out what's called the empirical formula. And so we've learned about chemical formulas, right? So for example, an example of a chemical formula would be something like NaCl, okay? But an empirical formula, by definition, okay, is going to be the lowest whole number ratio of atoms in a formula. Lowest whole number ratio of atoms in the formula. So what that means is the empirical formula might not necessarily give us the whole picture. It's not going to blatantly say what the exact sample is, but it will tell us the lowest whole number ratio of atoms in that formula, and from there we can make deductions about what that possible formula could be. So let's go ahead and talk a little bit about how to calculate the empirical formula if we're given percent composition. So if you're following along on my guided notes sheet, you'll notice that there's a problem that's listed here. If you're not, I'm going to write it out right here. But I want to find what is the empirical formula, which I'm going to abbreviate as EF, okay, for a compound who has the percent composition of 25.9% nitrogen and 74.1% oxygen. So I want to know what's the empirical formula. So in order to calculate empirical formula, there's actually this cute little poem that helps you remember the different steps of the empirical formula. So the first step, step number 1, is going to be percent to mass. So essentially, we're going to take these percentages that have been given to us, and we're going to convert those to a mass value. Now, because we're working with percentages, which literally means of 100%, then it's most easy to remember or to assume that our sample is 100 grams. Okay, that means that we can convert those percentages directly to grams. So for example, this would mean that we have 25.9 grams of nitrogen and we have 74.1 grams of oxygen in our sample. Okay. The second line of our poem that's going to help us remember how to complete this problem is mass to moles. Now, you might be thinking this doesn't rhyme just yet. It'll get there, okay? So we're going to convert from percent to mass, which we've done, and now convert from mass to moles. So 25.9 grams of nitrogen essentially is how many moles of nitrogen, and 74.1 grams of oxygen is how many moles of oxygen, okay? So to do that, we need our gram formula mass from the periodic table. okay, or our atomic mass from the periodic table. And so we have 25 point, or I'm sorry, let's set this up using the mole equation, okay? And so we have X moles is equal to 25.9 grams of nitrogen divided by 14.01 grams per mole, right? Directly from our periodic table. And we have X moles is equal to 74.1 grams of oxygen divided by 16.00 grams per mole of oxygen. Okay, so from there we can now calculate these. So 25.9 divided by 14.01 is going to give me a total of 1.85 moles of N. And for oxygen, it's going to give us 74.1 divided by 16 is going to give me 4.63 moles of oxygen. Okay, so now we know the relative number of moles of nitrogen compared to oxygen. But again, a chemical formula isn't just the relative number of moles, it's the ratio of mole to mole. So we're really looking at what is the ratio of N to O. And in order to get that ratio, we are going to complete our next step, which is divide by small. Okay, so percent to mass, mass to moles, divide by small. And so what that means is we want to find the lowest, okay, we want to find the ratio, and we're going to divide by the smallest mole value in order to find that. So for N, I have 1.85 moles. And for O, I have 4.63 moles. And we're going to divide by the smallest mole value, which is 1.85, which is going to give us 1N for every, okay, 4.63 divided by 1.85 is going to give me 2.5. Okay, so now we know that for every 1N, there are 2.5 oxygens. But if I were to stop here and write my chemical formula as is, it would be this, NO 2.5. And immediately that should be problematic for you because we don't ever see partial atoms in our chemical formula, right? So we can't have this 0.5 value there. So the last step of our poem is going to help us eliminate any of those 0.5 values or 0.25 values or 0.33 values that you might end up with. And our last step is going to be to multiply till whole. So our whole poem is percent to mass, mass to moles, divide by small, multiply till whole. And again, it ruins the poem, but I'm going to add a note here. This is if necessary, okay? Not every step, not every problem that you do is going to end up with this weird number ratio. You might be able to stop at step 3 for some problems. Okay, and we'll talk about the rules for rounding in just a moment. So in order to get this to the nearest whole number value, we're going to multiply all of our values. So N, again, we had 1, and O, we had 2.5. We want to find the lowest common multiple. Is that the right word? I don't know. But we're going to multiply here in order to get that O to be a whole number. So the easiest way to get this to be the whole number is to multiply this by 2, which is going to give us a total of 5. And we're going to multiply the N by 2, which is going to give us a total of 2. This is going to give us our final formula, which is N2O5. And you'll notice that this is still considered empirical formula, right? The 2 cannot easily divide into that 5 value, okay? So we now have our empirical formula. Let's just really quickly, before we bounce back to our initial problems, just check in about how to round. So this last step, this multiply till whole step, this is not going to, again, happen that frequently. So I generally use, if numbers come out to be 0.5 or 0.25 or 0.33, that's typically when you're going to do the multiply till whole, because we'd multiply this by 2, this by 4, and this by 3 to get to those nearest whole numbers. If you get something like, let's say, 1.93 at the end, I would say this would round up to 2, okay? If you get something like 2.06, I would say it's safe to round this down to 2. You don't want to try to figure out, right, a crazy numerical value to multiply these by. Again, if it's going to be a multiply to whole, it's going to be one of these nice, easy to multiply values. Okay, it is fair to round. I usually say if it's below 0.1 or above 0.1, or I'm sorry, below 0.1 to round down, and if it's above 0.9 to round up. Now let's go just as a check to check back and answer our problem, which is going to be which bottle is going to be the safe bottle to drink. So we need to bounce back to those initial percentage values, okay, which are going to be, again, bottle 1, which is made of 11% hydrogen and 89% oxygen. And bottle number 2, which is going to be the 5% hydrogen and 95% oxygen. So again, first step, percent to mass. So for H, that's going to give us 11 grams. For O, that's going to give us 89 grams. For bottle 2, H, 5 grams, and O, 95 grams. And I actually should have said this, if you want to give this a shot on your own to test your knowledge, feel free to pause the video here and then come back and, double check your answers. Okay, but if not, let's continue working together. So now we have our mass values. We're going to convert those to moles. So in order to convert to moles, right, we are going to get X moles equals 11 grams divided by 1.01 grams per mole. Okay, X moles equals 89 grams divided by 16.00 grams per mole. And for bottle 2, we're going to get X moles is equal to 5 grams divided by 1.01 gram per mole. And O, X moles equals 95 grams divided by 16.00 grams per mole. Okay, so 11 divided by 1.01 gives us 10.89 moles. And 89 divided by 16 gives me 5.56 moles. And for our second problem, 5 divided by 1.01 is going to give me 4.95 moles. And 95 divided by 16 is going to give me a total of 5.94 moles. Okay, or did I do that right? So 95 divided by 16. I just wanted to check in. Yes. Okay. So from here, what we're going to do is we're going to divide by our smallest mole value. So divided by 5.56 divided by 5.56 gives us a 1:2 ratio, right? 10.89 divided by 5.56 gives us 1.96. Again, at that point, I would just round that value up. So it's a 1:2 ratio. For our values over here, we're going to divide by 4.95, divide by 4.95, and that's going to give us a 1:5.94 divided by 4.95, about 1.2. And again, at this point, there's no sense in multiplying that out. I would probably round that down. That's probably the threshold, 0.2 round it down, 0.8 round it up, and this is going to give us essentially a 1:1 ratio. So what then is the empirical formula? Okay, the empirical formula for bottle number 1, our final answer for that empirical formula is H2O for bottle 1, and for bottle number 2, it's going to be HO. And again, the question is, which one of these was safe to drink? Well, our chemical formula of water is H2O, so that's looking good. HO might not be something on its own, but this is the empirical formula. It's the lowest whole number ratio. So that means it could be, it's a 1-to-1 comparison. So if I had 2, it would be H2O2 or H3O3 or H4O4. Okay, and H2O2 is hydrogen peroxide, which would not be good to drink. So our bottle number 1 is the safe bottle to drink. All right, everybody, I will see you guys tomorrow to practice empirical formula. Have a great day.